So we're given the scenario in 1656 where a man named Otto von G carried out a dramatic demonstration of the effect resulting from evacuating air from a container. It is the basis for this problem. Two steel hemispheres of radius 0.410 meters with a rubber seal in between are placed together and air is pumped out so that the pressure inside is 13 millibar. The atmospheric pressure outside is 940 millibar. Calculate the force required to pull the two hemispheres apart. So what's actually holding these hemispheres together in the first place? Well, we're given this pressure of inside the sphere being 13 millibar. Well, pressure is defined as force per unit area, so this 13 millibar must be supplying some force directed towards the outside of the sphere per unit of area. This 940 millibar must be supplying a larger force per unit area that overcomes this inner force and ends up pushing the two hemispheres together. Now you first might think that we may need to think in the three-dimensional to solve this problem, but that's actually not the case. In fact, this problem is a lot simpler than it appears. Each one of these vectors will have an x component, a y component, and if you want to consider the 3D, a z component. But because of symmetry, if we're thinking about one hemisphere alone, because of symmetry, all these x or all these y and z components will actually cancel out, and the resulting vector, if you summed all of them together on this one hemisphere, will be one vector pointed inward towards the seam of the two hemispheres. Pointed inward towards the seam of the two hemispheres, holding this hemisphere against that hemisphere. And the other side will have the same thing, a resulting vector pointed inwards, a resulting vector pointed inwards towards the inside or towards the seam of the two hemispheres. But what about all these inner vectors, the force vectors coming from the 13 millibars inside the sphere? Well, they're going to experience the same thing. They're going to have one resulting vector. Because of symmetry, all the x or all the y and z components are going to cancel, and they're going to have one resulting vector pointed outward. It's not even that big. Pointed outward, away from the seam. And because of what I was talking about earlier, this vector, obviously larger than this vector, the inward vector, obviously larger than the outward vector, is what's holding the two hemispheres together. So what's the total force that we need to overcome? Let's say these are ropes attached to teams of horses. What's the total force I need to apply in this direction to overcome the force from the pressure holding the two hemispheres together? Well, as I said earlier, pressure is defined as force per unit area, and we can solve for the force by setting it equal to the pressure times the area. Now, what's the total force of this vector going inward? Let's say on this side, this hemisphere, or on one hemisphere. We'll call that force outside. Force outside. That's the force from the outside pressure pushing inward on the hemisphere equals pressure outside times area. Well, what about force inside now? Well, force inside equals pressure inside times area. Now, I said earlier that we don't have to think in three-dimensional. And that applies to our area as well. Since we're only thinking in the two-dimensional, instead of thinking of the area as a hemisphere, we think of the area as a circle. And now if you don't understand what I'm saying is, like, instead of imagining that these are two hemispheres pressed together, imagine that these are two circular discs pressed against each other. And then our radius doesn't apply to a sphere or hemisphere, but now our radius will apply to looking at that hemisphere as a circle. And if we calculate the area of that circle, we can use that area in determining our force. And that's our force in the x direction holding the two hemispheres together. So our radius was equal to 0.410 meters. So the area of each one of our now circular discs instead of hemispheres will equal pi r squared, because that's the area of a circle. So pi 0.410 meters squared. So if we go back to look at our equations here, and let me select these right there. We have our equations now. Now we know our pressure outside, pressure inside, and we know our area because they're the same for both of those. So we can go ahead and start to calculate what our forces are. But we ought to keep in mind this up here too. Let's see if I can take this. Since this takes a whole process of trying to find how to convert millibar into newtons per meter squared, they give it to us right here. So we can go ahead and throw that conversion in our equation too. And I'll show you what I mean. So let's call the force that we have to overcome, we'll call it force total equals the force outside minus the force inside. And then we have equals, well, what's force outside? Force outside is pressure outside times area. Well, pressure outside was 940 millibar times our conversion, 100 newtons per meter squared over 1 millibar times our area, which is pi 0.410 meters squared. And you see millibars will cancel, meter squared will cancel, and then we're going to be left with newtons, which is our units of force. Now what's the force in? So we got to go minus the force in, which is the pressure on the inside, which was 13 millibar, times 100 newtons per meter squared over 1 millibar, times the area, pi 0.410 meters squared. Alright, so you can plug this into your calculator. Let me zoom out so you can see this. You can plug that into your calculator, and what you'll get is 48,955 newtons. Let's use that again. 48,955 newtons. And that is the answer to part 1 up here. 48,955 newtons. Now, that's the force required to pull the two hemispheres apart. With two equal teams of horses that are attached to each hemisphere, to the hemispheres, if each horse can pull with a force of 1,390 newtons, what is the minimum number of horses required? What is the minimum number of horses required? So we have 48,955 newtons, and we have our sphere. Let's draw in the middle. We have our sphere, and we have a team of horses pulling this direction, and a team of horses pulling this direction. And you might think, that since we have 48,955 newtons going this way, that we only need 36 horses, because 48,955 divided by, each horse can pull 1,390 newtons worth. This will give us a number of 35.2, which is approximately 36 horses. I'll put horses there. Newtons per horse. That way our units work too. So if we have two teams, or if we have a team of 36 horses, you would think that'd be enough. Well, it's not, because if you attach 36 horses to just one side, pulling this direction, what that's actually going to do is it's just going to move the sphere at some speed, because you have nothing anchored in the other direction. Now, if you put 36 horses going this direction, that can overcome this vector, this force, and then you put 36 horses going this direction, that can counter and maintain the sphere in place while the other encounter the force of the other 36 horses, you can then pull the sphere apart. But you actually don't even need these 36 horses here. Now, the answer to the question is 72 horses. But technically the answer is wrong, because you could attach this to a tree. I can draw a better tree than that. Let's say you attach the rope or cable or whatever it is around a tree. And then you have how the hell do you draw a horse? That's a dinosaur. Alright, and then you have 36 horses pulling this direction while a tree holds it place. The harder these horses pull, the more force you'll have going in this direction as well, or at least on this rope. So you can equal the same amount of force as 36 horses just by attaching one side of the sphere to a tree and driving these horses on this side. So even though the problem says you need 72 horses, you actually only need 36 and a tree. And that's why I'm right.